Hello everyone, my name is Dr. Satyanarayan Rao, and in this video I am going to talk about the Poisson's process, and it is one of the most important and fundamental concepts in probability theory that actually helps us to model number of real-world situations. For example, the number of customers that go into a supermarket or the number of car that actually passes by in a highway. All this actually follows the Poisson's distributions. Historically, actually, the Poisson developed this distribution to actually study legal cases or court cases, jury decisions, but it actually eventually made its usage into other fields. For instance, it was used to model how many soldiers could be killed by horse kicks. In the olden days, the soldiers used to go with the horses and swords. So in the Prussian army, this Poisson's distribution was actually used to model how many soldiers would be killed by horse kicks. And later, astronomers have used Poisson's distribution to understand how to count number of stars in the universe or other celestial bodies. And now it explains a lot of other things from radioactive decay to DNA mutations. In this video, we will understand the Poisson's distribution with a very simple example of job applications that arrive for an open position. Let's say there was a job posting on LinkedIn, and how does the application arrive actually follows Poisson's distributions. And let's say that I apply to a job and there are on average 20 applicants every day applying to this job. And let's say this job is open for 15 days. And so every day on average 20 applications arrive to the industry or the company, and one of them is my application. This process actually can be modeled as a Poisson's process. If you plot it, it exactly looks like the Gaussian distribution, and this is usually modeled where the events occur randomly, like the applications, they arrive randomly. There is no link between the applicants. I can apply from India and someone can apply from China to the same job application or to the same job opening. And I do not know when and where people apply, and each application is independent. One person applying does not influence the other, but sometimes it does. If you have like friends you recommend to the same job openings, then it may become complex, but let's assume that most of the time the job applicants are independent. They apply through LinkedIn or some social media platform, and each job opening will have a average rate, which we refer it as lambda here. This lambda tells me that what is the average number of applications that come each day. But it doesn't mean that every day exactly 20 applications come. Sometimes you may get 15, sometimes 5. If it is on weekend, then people have more time to apply for more job openings. So you may well exceed the average rate. You may get 25 or 30 applicants also. But on average, it's the 20. And so this is the Poisson's distribution we have, which actually tells me what is the probability that we exactly get k application, where k is the number of job applicants. And so p of k is lambda power k exponential to the power of minus lambda divided by k factorial. So this if you plot this, it will exactly look like a Gaussian, and you have the average value number of applicants at the center, and you have both sides from the average. But the beauty of this distribution is that you have only one parameter to describe it. Unlike Gaussian, you have in the Gaussian distribution you have mean as well as the standard deviation. But here if you see, there is only one parameter lambda, and here you have the distribution that actually explains this kind of processes. And this equation actually emerges from binomial distribution. So it has a physical meaning that when we divide time into tiny intervals, the exponential factor comes naturally. And so this is a natural pattern, and actually not just the job arrival of job application, but lot of other processes also follow Poisson's distribution. For example, if you are plant breeding, the seed germination, the number of seeds that germinate over time follows this kind of distribution. Some seeds, today there may be 50 seeds that germinate, tomorrow 75, but on average the number of seeds that germinate will have a fixed value, and we can describe such processes including lightning strikes. Even actually the Poisson's distribution was initially used to study in the earlier days to actually count the number of stars in the universe. This is a fundamental pattern that describes a random yet it has a steady rate, like the job application, for example. So having understood the Poisson's distribution for modeling, how we can use it to model how job applications arrive, I should also mention that there's actually a related concept for what happens after all applications are received. When the HR begins processing these applications, the service time, if we have to model the service time or the waiting time, these kind of processes usually follows a distribution called as exponential distribution. It is another fundamental concept in probability which follows memoryless property. Even though the job application is the same underlying process, why the arrival rate is Poisson and the service time is exponential. So for arrival, we are actually counting the number of discrete events, that is the applications that are being submitted in a given time interval before the deadline, how they are distributed. Or we are asking how many applications will arrive in the next hour or next week or next month or in a given time. When we look from the service side or the service time, we are measuring the continuous time it takes to complete one event. For example, how long will it take to process this single application? And so this actually follows the exponential distributions. But for this video, I think we have covered the essential of Poisson's process or Poisson's distributions, how it models the random arrival of events at a constant average rate. In my future videos, maybe I will talk about exponential distributions and we will explore other concepts. Till then, thank you for watching my video. Enjoy life. Thank you.